The last example is about a game. How did AlphaGo win? We're not going to really talk about the AlphaGo's algorithm, but we're going to introduce the fundamentals by looking at a much simpler game, the tic-tac-toe game, also known as noughts and crosses or X and O's. So basically there are two players. One writes X and the other one writes O onto this 3x3 board. The player who succeeds in placing 3 of their marks in a horizontal, vertical, or diagonal row wins the game. Usually we let the computer place X first. Okay, so for example, computer place X first, and the other one, say the human, place O here. Right, next, here's an X, and where would you place the next knot? Here. Alright, so who's gonna win? Well, what if the computer places a cross here? It's hopeless for the human, right? No matter where you put this knot, put knot here, the computer can place X here. So that wins the game. And the game tree for this game is like this. We start from an empty board. And the first move is given by the computer to place a cross. And there are 3 distinct possible places to go. I say distinct means although it looks like we have 9 options, but actually we only have 3, because it makes no difference if we place cross here or here or here or here. These 4 positions are equivalent, so we consider them as one option. Okay, for the same reason, these 4 corners are also equivalent. Therefore, we only consider this case. Alright, and the next move is made by human. And so for human, we have that many different options to place the next knot. Right, and then the next turn will be computer, and so on and so forth. And for such a small game, what do we get? We have that many possible board layouts. It means that for each position, we have 3 possible status, either cross or not or blank, right? So for each position, we have 3 options, and there are altogether 9 positions. So it's 3 to the power 9. There are that many possible board layouts. And there are 9 factorial possible games. And games means different sequences for placing the cross and knots on the board. So notice that this is such a small game, only 3x3, comparing to the game Go, which is 19 by 19. So exhaustive search is certainly not a very smart solution. And we don't have the time to try out all the possibilities before we make the next move. So what do? Here is the minimax strategy. So which means we evaluate each candidate position and assign each position a specific value, a number. And the human is always trying to minimize that value. And while the computer is trying to maximize it. So basically we're considering ourselves as the computer. So we try to maximize it while the human is trying to minimize it. Okay? So the key is to design a good function that can quantify the goodness of a position. Quantify means to map a position into a number. And this is a very simple example of such a function. To the computer, this number is, say, the larger the better. And the human will try to make this number as small as possible. So for example, we can simply define this function to be the win number. W is the number of potential wins at position P. So it's the win number for a computer minus the win number for a human. And here, a win means a line that is possible to win. So, for example, if we have the board like this, and for the computer, we're going to have 1, 2, 3, 4, 5, 6 wins. And for the human, we only have like 1, 2, 3, and 4. Only 4 wins. And therefore, the corresponding function value would be 6 minus 4. That gives 2. Alright, now let's get back to the game tree. And as a computer, we start from an empty board, and we would like to decide the best position for our next move, either this one or this one or this one. Okay, now let's try to look ahead for 2 steps and evaluate each of these positions. Okay, for example, for this one, the function value is 1 because for the computer, we're going to have 1, 2, 3, 4, and 5 wins, right? And for the human, we have 1, 2, 3, 4. 4 wins, right? So the difference is positive 1. And for this one, we already calculated before, it's 2, right? And so on and so forth. So you can try to calculate each one and get those numbers. All right. So before this level, at this level, it's the human's turn to decide the next move. And we assume that as a human, we would always try to adopt the position with the minimum function value. So this is called the mean level for the human. So for example, if we are at this position, we have 2 options, and we would always choose the one with the smallest function values. So we're gonna make our next move here. Okay, if we are at this situation, we have 5 options, and we take the one with the smallest function value. That is, we're supposed to make our next move here. Okay, and this one, we're going to adopt this negative one. Alright, now let's trace back to the very first move for a computer. A computer will always take the one with the maximum value of the function, right? So this level is for the computer, is the max level. So we're going to have alternating max and min levels, right? For the computer to make the decision, it will choose the one with the maximum function value that gives 1. That means the computer would make its first move at this position. All right. So this is when we look ahead 2 steps only, and we must calculate all these function values and then trace all the way up to make the first move. And we say that a master can look ahead for at least 5 steps, right? And in Chinese we say 下棋看5步. That means what? That means that we're going to have to make more computations. When we go deeper, the amount of calculation grows exponentially. Means that it will take much more time to finally decide one move. So if we have to make a decision in a given time period, so we know in such kind of games, you can't keep thinking forever, right? So we only have a very limited time to do the calculations, and therefore we cannot go too deep. So on the other hand, the faster we can run the checkings, the deeper we can go, right? Now, here comes the pruning trick. First, the alpha pruning for the computer. If it's a time to make a decision for the computer and we are at a situation like this, what is this situation? It means that we have already completed searching this subtree and update the maximum value to be 44 at this moment. And then we begin to search the other subtree. And the root of this subtree is at the min level. And suppose that we have already complete searching of this subtree and we update the current min number to be 40. And if this 40 is smaller than or equal to this 44, and that means we don't have to go through this subtree. We can simply cut the whole branch. Why? Because the value of this node doesn't matter. Now let's check out. We have two conditions, right? One is that if this number is greater than 40, or if this number is smaller than 40, right? So let's say if this one is larger than 40, what's going to happen? Since this is the min level, if this number is larger, this 40 will not be updated, right? Because it takes the minimum. And it will not affect the final result of this max level. So if it's greater than 40, it doesn't matter. And if it's smaller than 40, then this number is supposed to be a smaller number. But keep in mind that we're making decision for a computer at this max level. And we're supposed to take the maximum value. This current number is already smaller than 44. And if this one is even smaller, it doesn't matter. It will not affect this 44. And therefore, if we are updating from left to right and realize that at the min level, this one is smaller, then we don't have to search this subtree. You can simply cut it. This is alpha pruning. And beta pruning is for the human. Okay, it's in this situation. If we are trying to make a decision for the min level, and we have completed searching of this branch and updated current minimum number to be 44. And then in the next branch, we have already updated this max number to be 68. And this 68 is greater than this 44. Then for the very similar reason, we can simply cut this branch. Because no matter what this number is, it will not affect the final result of this min level. So I'm not going to go through the details for this one. Everything is just similar. So during the search, we apply alpha-beta prunings alternatively. So alpha-beta pruning is when both techniques are combined. In practice, it limits the searching to only big O of square root of n nodes, where n is the size of the full game tree. So it's quite a significant improvement. Alright, and so much about the backtracking, and you're supposed to have your second research project. It's about safe fruit. The story is like we know that there are some tips telling us that some of the fruits cannot be eaten together, okay, and otherwise it will cause serious problems. So you're given a long list of such tips, pair of fruits that not supposed to be eaten together, and a big basket of fruits. You're supposed to pick up those fruits so that it's safe to eat any of them. It's a typical application of backtracking, and I hope you enjoyed it.